Alright, so as we've seen in class, the gravitational potential energy between two objects of mass m1 and m2 separated by some distance r is given by minus gm1 m2 divided by r. So this is the expression for the gravitational potential energy between two masses. Alright, I'm just going to briefly describe how this formula comes about and how it relates to the earlier formula for gravitational potential energy that we'd seen throughout this course, which was mgh. So let's just quickly review how we derived the expression for gravitational potential energy earlier. So if you look back at your notes, this is a definition, this is a derivation that's simple enough that I did in class. What we did was we chose the zero level of potential energy to be on the ground. So we said that at y equals 0, u we arbitrarily chose to be 0. And then we asked what would the potential energy be at some height y, say y is equal to h, what is the potential energy going to be over there, right? And so how did we figure out the potential energy? We used this expression, which is also the definition of potential energy. Delta U equals the negative of the work done by the conservative force. So if we choose the ground to be, if we choose the height h to be the final position, ground to be the initial position, the change of potential energy is clearly u minus 0, and that is equal to minus the work done by the gravitational force in taking the object from, as the object goes from the lower to the higher position. So the gravitational force we assumed was constant mg, and the object is moving through a distance h. The angle between the gravitational force and the displacement is 180 degrees. So the work done would be, using the simple formula for work, it would be force multiplied by distance multiplied by cosine of 180 degrees. One cosine 180 is -1, and so you get u equals mgh, and this is how we derived the expression for gravitational potential energy. Clearly, in this expression, uh, we assumed that g is constant. So that's a crucial assumption. We assume that g is constant. And so this expression is only as good as the assumption that g is constant. So as soon as we can no longer assume that g is constant, this derivation pretty much breaks down. All right. What do we do if g is not constant? So now we have a situation. Let's say this is the Earth, right? And let's say that an object is at a pretty great height compared to the radius of the Earth, right? Okay, so we are talking about heights which are comparable to the radius of the Earth now. Previously, we were talking about heights which were very, very small compared to the radius of the Earth. All right, so we have an object over here, um, and we want to find out at a certain height, we want to find out its potential energy. Let's say that our object is over here. As I mentioned, the height that it is above the ground is comparable to the radius of the Earth, and let's say that we are measuring distances from the center of the Earth. That's the more convenient thing to do here, rather than from the surface. So the object is currently at radius r measured from the center. All right, now we are going to follow exactly the same procedure as we did in the previous derivation, right, that I did right now. We are going to choose the zero of potential energy somewhere. Where should we choose the potential energy to be zero? It turns out that a great place to choose the potential energy to be zero is r equals infinity. So at a very, very large distance away from the Earth, when r is equal to infinity, that's a great place to choose the potential energy to be zero. All right, so we've chosen the zero level of our potential energy. We just now need to find out what is the potential energy at some arbitrary r. That's the goal here. We're going to follow exactly the same mathematical steps. So we will use this expression, delta U equals minus work done by the gravitational force. You can see how this will be different. The work done by the gravitational force is just going to be a little more complicated because the gravitational force is not constant, like in the previous case. All right. So we'll assume that the infinity is where the object started and it ends up at distance r from the center. So delta u would be u final minus u initial, so that would be u minus 0. And let's see how we would calculate the work done by the gravitational force. Remember, the gravitational force is always towards the center of the earth, right? And let's say the object has mass m, the earth has mass capital M, radius r. All right, and the gravitational force, I'll just write it as Fg, is directed towards the center of the earth always. Okay, so let's say that the initial situation is when it's at infinity, final situation is when it's at radius r, right? So what is the change of potential energy? I already did that, it's u minus 0. And now we have to do the work done. So the work done will be integral Fg dr. So this is one-dimensional work. You might remember from chapter 6 and 7 that in one dimension, the work done is simply the integral of the force over the distance. Right? This follows from the line integral definition of work, the general line integral definition of work, but we saw that the line integral just simplifies into an ordinary integral when everything is in one dimension. All right, so that is the expression. We just need to evaluate this. So u is equal to minus, what is the gravitational force? Now, if we adopt a sign convention where radially outward is positive, so that would mean the outward direction is positive, then the gravitational force is directed inwards, so it should get a negative sign. And what's the expression for the gravitational force when the mass is at a radius, at a distance little r from the center of the earth? According to Newton's law of gravity, it will be gmm divided by r square. So that's the gravitational force, dr. And what are the limits of integration? So the object is moving from r equals infinity. So one limit of integration would be infinity, and then it's ending up at r equals r. So that's the second limit of integration. I mean, I should have probably called this r as r final or something like that. So I'm using r both as the integration variable and also one of the limits of integration, but hopefully the meaning of that is clear. All right. So now all we have to do is just evaluate this. So this is just algebra. The two minuses cancel out. And so you have to do this integral. We could probably pull out the gmm. And so now we have to integrate 1 over r squared dr from infinity to r, right? The integral of 1 over r squared is just negative 1 over r. So we end up with gmm negative 1 over r infinity to r, right? All right. And you can use a property of definite integrals that if you flip the limits, then then it's a negative sign. So I can also write this as gmm. This is just algebra. There's multiple ways of doing this. 1 over r to infinity, right? All right. And so all that happened was that I flipped the limits. So now it's r to infinity, and as a result of that, the minus sign is gone. That's just a property of definite integrals. And then I can just plug in the limits. 1 over infinity is 0, so the answer is going to be 0 minus 1 over r. So the final answer is gmm over r, and that is the potential energy at radius r. So this is the expression for the potential energy of an object which is at a distance r from the center of the earth. And you can see that the zero level of potential energy in this expression has already been fixed. U equals 0 at r equals infinity. That's already built in to this expression. And that's it. So that's how we got it. So all that we did was we started with the same expression, delta U equals minus WC. The only difference was calculating the work was a little more complicated because we did not assume that the gravitational force is constant. Since you watched this far, I might as well just show you one other thing. This was not my original plan in making the video, but I just thought of it now. It shouldn't take too long. Suppose I have the Earth like this, and um, I'm considering 2 points, one of them on the surface of the Earth and the other one at a height h. All right. So I'm going to calculate the change in potential energy between these, the difference in potential energy between these 2 points, using the expression for potential energy that we just derived. U is equal to minus g m over r. All right. So let's call this point A and this point B. So what I'm trying to calculate is potential energy at B minus potential energy at A. I just want to see what that comes out to, right? And so B is at a distance of r plus h, and A is at a distance of r, which is the radius of the Earth. So you can try this on your own and see if you can figure it out yourself. Feel free to pause the video and work this out on your own. All right. So let's put in both UB and UA. So UB would be minus GMM over r plus h, minus UA is going to be minus GMM over r, right? All I did was plug in the appropriate distances. All right. Let's simplify this. So this is GMM over r. So what I did was these two minuses made a plus, so I put that out front, and then the other term is minus GMM over r plus h. All right, let's simplify that. So GMM, factor that out, 1 over r minus 1 over r plus h. Let's simplify this. So if you do a common denominator, you get GMM. Okay, yeah, if you do a common denominator, you get r times r plus h, and then you have r plus h minus r. So the r's cancel out, and so you get this expression GMM h divided by r times r plus h. This is the potential difference between 2 points, where one point is on the surface of the Earth and the other point is at a distance h from the surface. All right. Now, if we assume that, so this is our UB minus UA. So if we assume that h is very, very, very small in comparison to the radius of the Earth, then there is no harm in ignoring the h in the denominator. And so it just becomes, so the denominator is effectively just r square, because this r plus h is just essentially r. So in that case, this just becomes GMM h divided by r square, and I shouldn't say equals, I should say approximately equals. So I made the assumption that h is very small in comparison to r. All right. So now what can we make of this? So we know that this is gm over r square is just little g. So you can see that this expression is just mgh. And you can see that we've derived mgh starting from negative gmm over r for a situation where we're considering the potential energy difference between 2 points, where one point is on the surface of the Earth and the other point is at a small height above the surface.